Hi guys, in this video I'm going to talk about high pass filters. Here we are specifically focused on passive first order ideal high pass filters. Okay, let's dive deep into the topic. First of all, I want to show you the magnitude frequency plot of ideal high pass filter. As you can see, here it is. Here, the x-axis represents omega, which is the frequency, and the y-axis represents magnitude. And there is an special point omega c, which we name as cutoff frequency. Okay, right. Then, as you can see, this is an ideal high pass filter. So, high frequencies are passed without any attenuation and low frequencies are attenuated. Okay. Now, there are some special facts that I want to specify here. The first one is this plot is for an ideal high pass filter. And the second one is we can observe an steep attenuation here. Okay. Right. Then the third fact is low frequencies are passed and high frequencies are attenuated, just as we discussed before. Okay, now we are going to observe the circuit arrangements that we can draw for an ideal high pass filter. Actually, there are two circuit arrangements. First one is this. Here, you can observe the voltage source and the capacitor and the resistor. The input voltage is Vi, whereas the output terminal voltage is Vout. The capacitance is C and the resistance is R. Okay? Then the frequency domain impedance associated with the capacitor is 1 over C omega. The impedance associated with the resistor is just R. Okay? Right. Next, the second circuit is this. Here, as you can observe, there is a small change compared with the first circuit. Here we are using a resistor and an inductor. Okay, right. Now, here, the input voltage waveform magnitude is Vi and the output terminal voltage is Vout. Okay. Next, the resistance is R and the inductance is L, whereas the impedance of the resistor is just R and impedance of the inductor is L omega. Okay, right. Now, the next big question is why these circuits are called as high pass filters. Okay, actually, that is the question, right? So, now we are going to observe why is that. First of all, I want to take the first circuit on your right hand side. Okay, right. So, if we observe the behavior of the circuit at high frequencies, it is like this. Here, we are considering the impedance of the capacitor because its impedance is the frequency dependent impedance compared with the impedance of the resistor because there is omega here, right? Okay, so at high omega, Cc is equals to 1 over C omega. Okay, when omega is high, this whole term is low, which means Vc the voltage of capacitor is low. That is because VC proportional to CC. Okay, right. So, whereas VC is low, it means VR is high. Here, VR corresponds to the output terminal voltage of the circuit, which is V out. Okay, so V out should be high. Okay, so next we are going to observe the behavior of the circuit at low omega. So, at low omega, the impedance of the capacitor CC is equal to 1 over C omega as previous, and we are interested on low omega, and when omega is low, this whole term is high. So, it means we see the voltage across the capacitor is also high. According to the voltage dividing principle, VR should be low, which means the output also should be low. So now, when we consider about this whole details, we can come to the conclusion that when the frequency of the input voltage waveform is high, the output terminal voltage is passed without any attenuation. And when the frequency of the input voltage waveform is low, the output terminal voltage is attenuated, which means this circuit is working as an ideal high-pass filter. Okay, I think you got it. Right. Next, we are going to look at the second circuit. Right? Okay. As same as before, at high omega, here we are directly focusing on the impedance of the inductor. And because here the impedance of the inductor is frequency dependent. Okay? Right. So when omega is high, this whole term is high. So because of that, VL, which is the voltage across the inductor, is also high, which means V output also high. Then at low frequencies, the impedance of the inductor is CL equals L into omega, and when omega is low, this whole term is low. It means VL, the voltage across the inductor, is low. It yields V output is also low. So now, according to all these details, we can get the conclusion that when the frequency of the input voltage waveform is high, the output terminal voltage is passed without any attenuation. And when the frequency of the input voltage waveform is low, the output terminal voltage of the circuit is attenuated. Okay? So we can come to the conclusion this circuit is working as an ideal high pass filter. Okay, now we are going to analyze the two circuits we discussed above. First, we are going to analyze the circuit on your right hand side. We are going to derive the transfer function of the circuit in the Laplace domain, which is Hs. So Hs equals V output divided by V input, and we can write this as R, which is the resistor, over R plus 1 over Cs. Here we are using the voltage dividing principle. Then we can rearrange this as RCS over RCS plus 1. We can rearrange again this as S over S plus 1 over RC. Okay. And we can simplify this term like this, where we substitute omega c instead of 1 over RC. We can come to the expression S over S plus omega c for this circuit. Okay, now we are going to talk about the second circuit. Here, again, as previous, we are going to derive the transfer function in the Laplace domain, which is Hs. So Hs equals V output divided by V input as previous, and we can write this Hs like Ls over Ls plus R. We can rearrange this as S over S plus R divided by L. By substituting omega c instead of RC, we can substitute omega c instead of R divided by L. We can come to the expression S divided by S over omega c. So, now here is a special point. Do you see these two expressions are common for both circuits? Okay. Only the value of the omega c is different when compared with each other. Right? Just keep that in your mind. Right. Okay. Now our next big task is deriving the frequency domain transfer function using the Laplace domain transfer function. Okay. We just have to do some small thing. We only have to substitute j omega instead of s to guess the frequency domain transfer function, which is h of j omega. So h of j omega equals j omega divided by j omega plus omega c. And we can attain to the magnitude of the transfer function h of j omega, whereas magnitude equals to omega divided by square root of omega squared plus omega c squared. And the base angle of the transfer function is 90 minus tan inverse omega divided by omega c. Okay, right. Next, for the second circuit, we can get the frequency domain transfer function as h of j omega, whereas it is equal to j omega divided by j omega plus omega c, just as before. Only the value of the omega c is different here. And the magnitude of the transfer function h of j omega equals omega divided by omega squared plus omega c squared. And we get the square root. Okay, right. Next, the base angle of the transfer function is 90 minus tan inverse omega divided by omega c. Right. Now we are going to talk about the plots, the magnitude frequency plot and the phase angle plot of the transfer function. But we are going to see and remind about the common formats we derived previously for both circuits. Here is the Laplace domain transfer function h of s for both circuits. It is s divided by s plus omega c. Here, omega c is different for each circuit. And the magnitude of the transfer function h of j omega equals omega c divided by square root of omega squared plus omega c squared. And the base angle is phi over 2 divided 5 over 2 minus tan inverse. What should be there? Omega divided by omega c. Okay? I think you remember about that. Right. Okay. Here, now we are going to see the plots. First, the magnitude frequency plot. As you can see here, we can observe the x-axis is omega, which is the angular frequency, and the y-axis is magnitude of the transfer function. Before coming to the plot, let's observe some maths. Here, as we derived before, the magnitude of the frequency domain transfer function h of j omega equals omega divided by square root of omega squared plus omega c squared. We can rearrange this as 1 over square root of 1 plus omega c divided by omega squared. Okay. So, our prime concerns are when omega equals 0 and when omega goes to infinity. Okay. First, we will look at when omega equals 0. Okay. So, when omega equals 0, the magnitude of the transfer function equals 0. So, we mark that point as this. Then, when omega goes to infinity, we can observe through this rearrangement, the magnitude of the transfer function goes to 1, like this. So, plot should be drawn as like this. Okay, I think you got it. The next big thing is the cutoff frequency omega c, and it occurs the value of the transfer function attained to 1 divided by root 2. It's a standard, okay? Right. Next, we are going to see the phase angle plot of the transfer function h of j omega. Here, the x-axis is omega, which is an angular frequency, and the y-axis is the phase angle theta. Okay? As we found before, theta equals 90 minus tan inverse omega divided by omega c. Our prime concerns are when omega equals 0 and when omega goes to infinity. First, we will look at when omega equals 0. When omega equals 0, the phase angle equals 90 because this term becomes 0. So, we will mark that point as this. And when omega goes to infinity, through the formula for the phase angle, we can attain to the conclusion theta goes to 0, like this. So, the plot is drawn like this. Okay guys, that is all about the theory part behind ideal, passive, first order high pass filters.